We are going to talk about service mesh in this video. One of the primary challenges with microservices design is the service-to-service communication. In one of the other video, I specifically talk about the good things and the bad things about the microservices. In that video, I specifically talked about the problem of how the integration complexity will become more complex when your number of services grows in the microservices. So service-to-service communication always have some challenges, and there are a lot of factors that we need to consider when we build a microservices application. So in this video, we are going to focus on what are the challenges we face in a service-to-service communication and how service mesh will manage those complexities. Let's get started. There are several factors that we need to consider when we build the inter-service communication, when we manage the service-to-service communication. Let's talk about those factors one by one. The first thing we need to consider is the network. So in a typical monolithic application, you have one single application and you might be having several modules within the application, like module A, module B, and each module might have its own business logic. Now, if the module A wants to talk to module B, it is going to be just a simple function call. But in case of microservices design, if the service A wants to talk to service B, the communication has to happen over the network. And we all know that the network, when the communication happens over the network, there is a lot of challenges, right? And when it comes to network management, there are a few things that we need to consider. One of the things is we need to think about the service discovery. And we also have to think about the load balancing. So let's talk about one by one. Let's talk about service discovery first. So now if the service A wants to talk to service B, it needs to know the address of the upstream service. So at a minimum, the service A should know the IP and the port of the service B. So if the communication is going to be layer 4 communication, TCP based communication, then at the minimum, at least you need the IP and the port. If it is a HTTP based communication, then you need to know the endpoint, you need to know what are the headers that you need to send and what HTTP method you need to use to invoke that particular request. So that's a different story, but let's try to keep it to the minimum. So at a minimum, the service A should know the IP and the port of the service B. Now, most of the modern microservices applications usually runs in a container orchestration platforms. There are several container orchestration platforms available like the Kubernetes, Docker Swarm, or HashiCorp Nomad. So I have a different video that specifically talks about container orchestration and what are all the capabilities you will get by using such container orchestration platforms. Please watch that video for more details. But imagine, so these modern microservices applications usually run in those kind of container orchestration platforms. And those platforms make sure the IP and port are never static. So you can't just go ahead and hardcode the IP and port in the service A and then talk to the service B. That won't work. Because whenever you deploy a new instance of service B, the IP and port will change. Or if for some reasons, if the service B gets restarted because of some issues or anything in the service B, again the IP and the port will change. So the service A cannot rely on any of the static IP and port to talk to the service B. So this is where we need a system that specifically do the service discovery. Like we need some kind of a system that should keep track of all the IP and port related changes across the system, and then it needs to store some kind of a database about the changes. So that whenever the service A wants to talk to the service B, it should ask the database, okay, I'm going to talk to the service B. What is the IP and port of that? What is the current IP and port of that? And then it will get that value and then it will initiate the connection. So we need a system to specifically do the service discovery. Now let's talk about the load balancing. Now for the high availability reasons, most of the time, each services will not contain just only one instance. Most of the times you will have multiple instances running for each service. Say for example, service A mostly contain maybe like some 5 services, and service B might contain some 10 instances. Service D might contain some 30 instances. It's all based upon the requirement and based upon the load that it needs to be handled, right? Now, in case if the service B contains many instances, like, so if there are too many instances running, now we need a mechanism, we need a load balancer in between the service A and service B, and that load balancer can route the traffic to the appropriate instances. So it should be able to route the traffic in a round-robin fashion to all the service B related instances. So now, yeah, of course, you can go ahead and put a load balancer in between service A and B, and you can also put a load balancer between all the services, right? But at some point of time, you will end up with a lot of load balancers in your system. You will have to maintain a fleet of load balancers, and that is a huge maintenance overhead, right? So you need to manage all those load balancers, and whenever a new service comes into the system, you again have to go ahead and spin up a new load balancer for that. So it's going to be a huge maintenance overhead if you want to maintain a fleet of load balancers in your system. The next factor we need to consider is security. So security is as important as any other features in the microservices design. So when I say security, you need to have some kind of an authentication and authorization mechanism between the service A and service B. So it's going to have authentication and authorization. So when I say authentication, when service A wants to talk to service B, it should be able to authenticate the service B, and the other way as well. When service B wants to talk to service A, again there should be some kind of an authentication system. Now we can actually do this using the TLS based authentication. We can have some kind of a certificate authority issue the TLS certificates, and you can go ahead and configure the TLS certificates for each microservice. And whenever the communication initiated, it will make sure that the request is actually coming from the authorized service. Yes, that is still possible. Now, the problem here is, the challenge here is, you have multiple services running in your system, and you have to manage multiple TLS certificates for each service. When I say manage, you still have to make sure that the certificates are stored securely. Also, you need to make sure that the certificates are rotated properly. So you have to renew those certificates when they are about to expire. And just imagine how many services you will have in your system and how many TLS certificates that you have to manage, right? And what about authorization? So when you build your microservices system, when you have just a couple of services, which is fine, you don't have to make too much deal about the authorization. But when you have too many services running in your system, you need to have a proper access control system. You should be able to define which services can talk to which services. Say, for example, I should be able to clearly define in the system that the service A should be able to talk to service B, but the service B should not talk to service E. So that kind of access control rules should be defined somewhere. Otherwise, in case, just consider if the service A get compromised, then the attacker can get access to all the services in your system, and they can just bring the whole system down. So that's not the right way to do. So you should have a clear access control in place. The third reason that I want to talk about is resiliency. Resiliency means the capability of the system to handle the failures gracefully, and it also should be able to recover from the failures automatically as soon as possible. And imagine, for example, if service A is talking to service B, and for some reasons the service B is not able to respond faster, and it may not be able to respond at all. There are some problems in the service B, and the service B is returning failure responses. Now, in this case, the service A shouldn't just give up. It should do a retry, because most of the times in the network-based communication, the fault could be just a temporary fault. It could be a transient fault. So if the service A do a retry on the same request, there is a lot of chances that the service B might return a positive response. So that is something that we need to consider when we implement the resiliency. The next, another common pattern in the resiliency is circuit breaker. So that is one of the most common resiliency pattern people usually use in microservices design. And I have a separate video that talks specifically about the circuit breaking pattern. And I would highly recommend you to watch that video to understand that concept in detail. So mostly circuit breaking is used to avoid the cascade failures in the microservices architecture. So that is one thing that we need to consider. And the third thing that we have to consider in the resiliency is rate limiting. So we should have some kind of a system in place where I can go ahead and configure the limit of a request that a service can accept. Say, for example, if accidentally the service A is pumping too many requests to the service B, like it is sending some 1,000 or 2,000 requests per second to the service B, and service B may not be able to handle that much load, and it might eventually fail. So this is where I need to have a system. I should be able to configure saying, okay, the service B should always allow only 10 requests per second. And if there is another 11th request that is coming on the same second, then the downstream service will receive too many request error. So that is something that we have to consider when we implement resiliency in the microservice architecture. So till now, we talked about what are the factors that we need to consider when implementing the microservices design. What are the things that we need to keep in mind in the inter-service communication, right? But how do we implement all these capabilities into our application? So how can we implement all these infrastructure-related features into our microservices? So of course, you can go ahead and implement authentication in the system. You can go ahead and manage the TLS certificates on your own. Or if you want to implement the retry or circuit breaking, of course, you can go ahead and make some code changes. You can write a custom logic to implement the circuit breaking functionality. Of course, you can do all those things. But imagine that's going to be a managed maintenance overhead, right? Because developers are actually supposed to focus mostly on the business logic. Because one of the major concerns that the organization usually have is faster time to market. So you should be able to implement the features as soon as possible and release it to the production. But if the developers start to focus mostly on the infrastructure related features, then they cannot focus too much on the business logic. So the faster time to production is not that easy. So this is why developers should be always focusing on the business logic. The microservices, each individual service should also focus on fulfilling the business logic, not on the infrastructure related activities. Now, how can we delegate these functionalities to another system instead of developers worrying about the infrastructure related things? Now, one of the other solutions is, of course, you can go ahead and utilize some library which already available, which already implemented all these infra related features. Yes, of course, you can go ahead and grab that library, integrate that into each of your service, and you can use that. That's one of the good idea. But one of the strength of microservices is you can use multiple programming language in microservices. Like the service A could be a Node.js based application, service B could be a Java based service, and service C could be Python based microservice. Now, maybe there may be some libraries available for each programming language, which you can identify, grab it, and use it in your microservice. But these libraries may not give you a consistent behavior across the system, right? Because the circuit breaking functionality which is implemented in Node.js might have a different behavior compared to the one that is implemented in the Python. So how can we achieve a consistent behavior for these all infrastructure related features across your system? So that's the challenge here. So that's where service mesh comes into picture. So service mesh is actually another infrastructure layer in your system that will take care of all the service to service communication related capabilities. So that the developers have to focus only on the business logic, whereas the service mesh actually sits on another layer in your infrastructure and it focuses on all the communication related activities. But you might be wondering, how is it possible? Because if you want to implement authentication, you still have to make some changes on the service, right? So if you want to implement authentication, or if you want to implement the circuit breaker or retry mechanism, you still have to make some code changes on the service A or service B. Without that, how is it possible? That's one of the common question people might have. Now, this is where service mesh comes with another easiest solution, which is called Sidecar Transit. The word sidecar actually means the picture that I'm showing it in the screen. Just look at the picture. It is actually one of the vehicle, and you have a sidecar attached to the motorcycle. So wherever the motorcycle goes, the sidecar actually follows it. So that's exactly the same behavior that the service mesh is bringing into your application. So the service mesh will spin up a sidecar proxy for each of your service. And whenever it want to initiate a connection, for example, if service A wants to talk to service B, the communication will not happen directly. The service A will not talk to the service B directly. Instead, the service A will always talk to the sidecar proxy. And the proxy will know, based on the request, the proxy will know where to route the request, in which service it needs to route the request. And once it identified that, then the proxy will talk to the proxy of the upstream service. Again, The proxy will not talk to the service B directly. Again, it will talk to the proxy of the service B. Now, the proxy of the service B will forward the request to the service B. So the communication, inter-service communication is always happening between the proxies and not between the services. Now, it doesn't matter in which language you build your microservice. It could be a Node.js service, or it could be a Java or Python, but still this solution works because you don't have to make any code changes in your service. The Sidecar proxy will handle all the communication. So this is how the service mesh actually works, and it offers all the capabilities that we were talking about here. And there are a lot of common service mesh platforms available. One of the most popular platforms is Istio. So Istio is a service mesh platform which seamlessly integrates with Kubernetes. And there is another service mesh platform called HashiCorp Console that also has all the capabilities that we discussed today. So I have posted some reference articles in the description, which actually helps you to read about these concepts in detail. So today we talked about what are all the factors and what are all the challenges we face in the service-to-service communication, and how service mesh manage all those complexities. Thanks a lot for watching.
Audio Jungle.